When it comes to the radio, we all have some sort of vague understanding of how it works. We don't know exactly, but we've been told that somehow using electricity, we create these waves that self-propagate and we modulate them and send them over long distances, and they're received and transformed back into the sound that meets our ears for news, music, and any other form of entertainment. Well, the mechanisms behind these waves are a lot less complicated than one might seem. In fact, they're perfectly analogous to a simpler system that many of us have seen in an introductory physics course, and that being a mass on a spring. So today I'm going to show how, with using just a tiny bit of calculus, if we can understand the math behind the mass on a spring, we can actually understand in great detail how radios work. Well, what can we say about the mass on a spring? And don't worry about all those doodads and gadgets on the simulation. Those will all come into play later in this video. But overall, what are some broad things we can say qualitatively about the motion? It seems very obvious that it goes to this equilibrium point and immediately begins to slow down, as if there's some sort of restoring force pushing it back. And it slows down and slows down. Eventually, it stops. It turns around and it speeds up back toward the center. And it sort of oscillates right that. It goes up and down and reaching the same height each direction. Exactly. So what I'm going to do now is I'm going to take you through a derivation so that we can be much more physicsy and quantitative rather, about how we describe our mass spring system. And then hopefully, after I do that, the parallels to the video will start clicking in the back of your mind. So as I said earlier, we're going about to get more physicsy about it, and part of being more physicsy about it is starting with our model. So here I have a very crude, rough drawing of a mass on a spring with the mass at the bottom and the equilibrium represented by the red dot, like halfway-ish in between. And if we're going to draw a free body diagram, which just shows all the forces acting on our system, it's obviously just going to be one force acting in the upward direction. And when I say I want to be more quantitative about things, right, that just means we want to have, actual functional equations for our position, displacement, our velocity and acceleration at all times t. And what we know to find that out is all we know, Hooke's law, which is our spring force is negative kx, where k is some constant, and negative denotes that the direction of the force is opposite of the way that the displacement is going. We know Newton's second law. And so the obvious thing to do here is just combine them together and move things around. If we divide by mass, we can see, yes, as we've been saying, we have our restoring force, which is going to have our system accelerate opposite in the direction it's going. And if we just put them at the same side here, we're going to know that it's going to equal 0. The reason we move it on the same side of the equation here is because it makes things a little bit more obvious, right? When you solve a quadratic, for example, and you want to complete the square, it's sometimes easier to see what you're supposed to do when you move everything to the left side. And obviously, if we want to put everything in terms of x, well, we know for a little bit of calculus knowledge that our second order derivative of position with respect to time is the same as our acceleration. So what we want to find now is a expression for x of t, because if we have that, we can use the derivative to find v of t, a of t, and everything else. And I'll make things easier by letting omega squared equal k over m, where k is our spring constant and m is our mass. And our hint is that our omega squared is related to the chain rule, as I'll put up in a little sticky note right in a second here. Yeah, there we go. So when we take our two derivatives, we're going to factor out 2 omegas. So think about a function whose derivative is itself or related to itself, or its second derivative. You know what I mean? I'll give you a second to think about it. You got this. And even if you don't, I didn't get it right the first time either. Well, it's not an exponential. It's not a logarithmic function either. It's actually a trigonometric function. Our x of t is actually a cosine omega t. I'm omitting the a, our amplitude scalar, because while it is technically part of the solution, it's just going to muddy our understanding if we put too many terms up here at once. We find our velocity by taking the derivative, and our acceleration by taking the derivative of that, or our second order derivative with respect to time. So you can probably start to see now how this is true. If we put negative omega squared cosine omega t in for the second order derivative, and then we multiply our equation for x right here by omega squared, it will in fact equal 0. I'll make that a little bit more obvious with this blue right here. Now that we have that, it's time to go back to our simulation, so we can see how the phase shifts between these different trigonometric functions relate to this mass's motion. We can talk about how this, now that we know it's trigonometric, we can talk about its wave properties, and now we can start to piece together how it might be related to the radio in some way. So now, as you can see, when we let omega equal to 1 by letting k and m both equal to 1, as we predict, it makes a wave pattern when we let the mass travel through space. There's a cosine function being traced out here. And now, when we plot acceleration along with it, we can see, as we've been saying all along, the restoring force is equal and opposite. And finally, we can see the speeding up and slowing down pattern that we pointed out earlier. It reaches some max height, and it speeds up back to the center, and it slows down as it goes away from it. And we can say that quantitatively by saying, look at the signs of the acceleration and velocity functions. If they're the same, well, then they speed up, and if they're not, it's slowing down. Okay, so now we're going to talk about LC circuits, and they are basically the foundations of our radio. It's only two components, a capacitor and an inductor. And if you don't know what those are, I'll explain it. As you can see here, a capacitor is made up of two plates, and what they do is they store charge. And an inductor, they're like electrical inertia. They're the constant resistance to whatever the current or the charge passing through per second through an area, basically. They resist it, whatever it wants to do. So let's say we have the circuit, right? And all we have is a capacitor. Obviously, the charge is going to want to equilibrate, right? And one's not a very nice number for this, so plus two, right? We have two positive charges. And like charges, they're going to repel each other. So what's going to happen in this little circuit is it's going to equilibrate, right? I'll use a little blue line to make it clear. So one of the charges is going to migrate, and it's going to be at equilibrium, right? It's going to be stable. Now, what if we had some sort of inductor? Well, what's going to happen is the charge is going to go, but at first it's going to resist, right? Because we go from no current to some current, and the inductor is going to want it to stop. But once it equilibrates, now the electrical inertia is going to want it to keep going, right? As if the car stopped and the seatbelt's, pressing against you, but your body still wants to keep going. The inductor is going to say, "Hold on, I want the current to keep going. I don't want the party to stop." It's going to all flow. You can also think about this, it's more accurate anyway in terms of energy, right? The capacitor had all the potential energy, and now the inductor has it. Now the inductor is saying, now I want to do what I want. And so now, as you can predict, right, we started with plus 2 on one side and it all went. Well, now we have plus 2 on another side. So it's going to do the same thing, except the opposite way. So now the plus 2 is going to go back to where it started, the plus 2 charge, and it's going to keep alternating and oscillating, just like our mass on the spring. Because as soon as it equilibrates, the inductor is going to say, hey, keep going. So now we have a system that's it's very reminiscent of a spring, the way it oscillates, right? But how do we prove this mathematically? Well, there's a little bit of a physics background necessary, but the following is true by the conservation of charge, and that would be the change in current over time, di dt, right? Sorry, took me a little second for it to load. The inductance times the change in current per second, or the time derivative of current, plus the charge over the capacitance of the capacitor equals 0. And I know this seems like Greek right now, but it should. I mean, these are foreign symbols, but it should remind you of something we did a little bit earlier. If you see, current by definition is the time derivative of charge. So if we're taking the derivative of current, it would be the secondary derivative of charge with respect to time. And the way we have it now, it looks just like the system we had earlier with our mass on spring system. So the mass is identical. So not only do they look the same, do they feel the same. In fact, mathematically, they are the same. They're both what we call simple harmonic oscillators. And here we have it all laid out very nicely. Now, if we let omega equal 1 for both systems, we can see that the motion of the mass on the spring is the same as the charge in the LC circuit that allows the radio to select for certain frequencies. And that is beautiful. I wanted to close off with some finishing thoughts because I thought it might still seem a little bit of abstract, right? We understand how waves come from a mass on a spring, and we understand how it comes from a circuit, but how does this circuit itself fit into the radio? Well, it acts sort of as a timer, right? Because we know we have omega, right, our frequency, and that's dependent on the inductor and the capacitor. And we can alter that frequency by moving the capacitor. So when you turn the dial on the radio, what it used to do, it would physically move apart the plates of the capacitor to alter the frequency, to alter what frequency signal the device would select for. So that's all you're really doing. You're altering the capacitance to mess with the frequency. In the same way you can mess with the spring constant of the spring or the mass on said spring to alternate that frequency. So that's how you change the frequency of the circuit to select for different input signals, and that's how your radio knows what to look for and what to play back to you.